session about lattice assumptions. We have three talks, one person, go online. Thanks for you. Yes, the first talk is by Vadim Lyubashevsky about lattice assumptions.
Go ahead.
Okay, thank you for the introduction, and thank you all for being here at 9 a.m. in the morning after the conference dinner. So in this work, I will be talking about like dense and smooth lattice and any genus, but for this talk, I will mostly be focusing on the dense part. We will start with some explanation about our lattices and lattice packings. Then we will get to this genus part, and then we will show the existence of good lattice packings in any genus. So let's get started. So a lattice can be described by a basis, and a basis is just like some n linear independent vectors, and the lattice then consists of all the integer combinations of these lattice vectors. And one important invariant of a lattice is the so-called lattice covolume or determinant of a lattice. And this is just the volume of any fundamental area of the lattice with respect to the tiling. And one example of such a fundamental area is the parallelepiped spanned by the basis vectors. And so this lattice covolume is just the volume of the parallelepiped. And note that such a basis of a lattice is not unique. We can always apply some unimolar basis transformation to the lattice, to the basis, and obtain another basis for the same lattice. But again, if we look at the volume of this fundamental parallelepiped, it's going to be the same because it's like really an invariant of the lattice. Okay, in our lattice we have some kind of discreteness. We have some distance between points, and the minimum distance between any two distinct lattice points is called the first minimum of a lattice. Another way to see this is as the minimum length or the length of the shortest non-zero lattice vector. And note that if we would like draw a ball of radius this first minimum, it contains at least 3 points, namely 0, the shortest vector, and the negation. It might also contain more, but remember this, that you need at least 3 points in this ball. That will become important later. We can turn any lattice into a lattice packing simply by placing balls of radius a half time the minimum distance around each lattice point. We know that they won't overlap because of this minimum distance, and this way you get kind of a nice sphere packing in the space. If we now have a look at the density of such a sphere packing, we can just look at what happens, it's just a repetitive pattern, so we can look like what happens per lattice point. So per lattice point we have this one ball of radius half times lambda 1, and also we have seen earlier that per lattice point we can have this fundamental area. So the density is simply the volume of this ball divided by the volume of this fundamental area, which is the determinant of the lattice. And if you look at such a density, well, of course, the density can be at most 1. The density cannot go above that. And in fact, this is what gives you Minkowski's theorem for this specific case. If you just write down the inequality out yourself. And what this does, it gives you an upper bound on the length of this first minimum with respect to the normalized determinant of the lattice. And of course, if you have such an upper bound, which we will here call like the Minkowski bound of the lattice, then the interesting question is, just from a mathematical perspective, is how close can we get to this upper bound? How good of a lattice packing can we find? And one answer to this is that given by the Minkowski-Lafka theorem, which says that in any dimension n there exists a lattice where the first minimum is at least a half times this Minkowski bound. So we can always reach this upper bound within a vector 2. And in the following 2 slides, we will give a quick proof of this theorem. And the main tool that we use for this, and the main observation, is that random lattices are in fact good packings. This is something that in the lattice literature we even have a heuristic for, namely called the Gaussian heuristic, which says take any kind of lattice that looks somewhat random, then we expect that the first minimum is going to be a half times this Minkowski bound. And this is also one of the reasons why these random lattices can be seen as like the hardest instances of lattice problems. Because, for example, for finding short vectors in these lattices, this really depends on kind of how good of a packing the lattice is to do this. So we have this like kind of good behavior on the average. We have a good packing on the average, but this is not a proof. Like this Gaussian heuristic is just a heuristic. But we could think like, if we can prove that we have a good packing on the average, then of course this implies that we have at least one good packing in general. And it seems a bit silly because like trying to prove something on the average over the space of all lattices sounds much harder than just proving the existence of one good packing, but actually it is a lot easier. And I haven't defined at all like what random is, but you can define a higher measure on SON of R, and the projection of this onto the space of lattices is kind of finite, but those details are not important for us. What we can do is we can look at the space of all lattices with a fixed dimension and a fixed determinant, let's say just one. And so why is it easier to say something about the average? Well, that's because we have these very strong results already by Lafka and Siegel from like 1943 and 1945, which says that if we draw some kind of ball in space, and we look at all the lattice points that fall inside of this. So we just count the lattice points that fall inside. And now we start to sample our lattice from this random distribution. Then what happens is that the number of lattice points that falls inside this ball is completely determined essentially by the volume of this lattice. We have one exception, namely we have this kind of 1 plus the volume, and the 1 just comes from having the point 0 always in there. In any lattice you have the point 0. Just to give an example of this, we can sample some of these random lattices, and indeed you see that the lattice points that fall in there is kind of, it now just looks like a random collection of lattice points with a certain, or like points in space with a certain density. And so the number of lattice points on expectation is just precisely given by this volume. And this is a very strong result, but it's kind of, like the proof is non-trivial, but the statement is in some sense very simple. And we can directly use this to prove the Minkowski-Lafka theorem. We can pick some ball of radius half time the Minkowski band, and by construction of this quantity, this ball will have volume 1. So if we plug that into our theorem above, we get that the expected number of lattice points in this ball is equal to 2, like 1 plus the volume is also 1. But if this is true on expectation over all the lattices, then there must be at least like one lattice that has at most 2 lattice points in this ball. So, yes. And if we look at this lattice, so we singled one out here, then we see that if you have at most 2 lattice points in the ball, then this ball must be of size less than the first minimum, because earlier we've seen that you have at least 3 points in the ball of radius more than the first minimum. So this is the lattice that we need, and this is the lattice that is gonna give you a good lattice packing in this dimension. So what we have done is we have, using these results about the average, we have shown the existence of a good lattice packing. Now let us quickly discuss about the lattice isomerism problem and the genus of a lattice. And then we will kind of try to repeat this argument from before. So the lattice isomerism problem is that given some basis of a lattice, we also look at orthonormal transformation of this basis. You can for now just think of some kind of rotation. And we look at the lattice spanned by this, which is just an orthonormal transformation of the other lattice. And if you get one of these lattices and an orthonormal transformation of the others, we call these two isomorphic, then the lattice isomerism problem asks you to recover this transformation. And note that here on the fly I kind of changed the basis of this second lattice, and that's needed because otherwise it's just linear algebra to recover it. Like in the previous step, if you just get B and O times B, that's simple to recover O. But you really also need this basis transformation to make the problem hard. Now maybe it's not so obvious why this is a hard problem, especially in dimension 2, where you could just say, okay, we just start to rotate the lattice a bit until they fall into each other, and that's very easy. Maybe it becomes a bit less trivial if you don't see these lattice points, so you only get these bases. And then you have to imagine that this happens in like 1,000 dimensions instead of 2. And it really seems to be a very challenging problem to solve. One small note, this solution to the lattice isomorphism problem is unique up to the automorphism group of a lattice, which are all those orthonormal transformations that act invariantly on the lattice. Okay, so we can try to build cryptography from this lattice isomorphism problem with the main idea that we can take some lattice with a nice structure that we can use, and we can hide this structure essentially by applying this orthonormal transformation. And this is an idea that has been brought up in two concurrent works, both presented at Asiacrypt, where in the first we kind of give a general framework where you put in any kind of decodable lattice, so any lattice in which you can decode, and we transform this into an encryption scheme. And similarly, you can have any lattice in which you can do Gaussian sampling, discrete Gaussian sampling efficiently, then we turn that into a hash and sign signature scheme. And the other work by Bennett and al. Kind of does the similar thing, but then they really focus on the lattice Z to the n. And one of the maybe more prominent examples is the Hawk scheme that was submitted to the additional call for signatures and also now made it to round 2. This is a highly efficient signature scheme that is not based on lib on unstructured lattices, but on module lib, so lib on module lattices. And essentially, since these works, there have been many other works appeared that use lib both for constructive things to build new cryptographic schemes, but also a lot of work on cryptanalysis has appeared. And in these schemes, we don't really look at the search problem of really recovering this orthonormal transformation, but usually it's more useful to have this distinguishing variant of the problem. This distinguishing variant gives you two non-isomorphic lattices, and it gives you one sample from the equivalence class of one of the two. And the question is, which one is the isomorphic to? So we get this lattice in the middle, which is an orthonormal rotation of one of the two, and you have to decide which one. And this is very useful because it allows you to kind of, in the security proof, replace one lattice by the other. And the usual security assumption of these schemes looks therefore as follows. One, we are given some like remarkable lattice, so like a decodable lattice or one which you can do this Gaussian sampling. And secondly, we need some kind of auxiliary lattice with certain good geometric properties. I'm a bit vague about this on purpose. And the idea is that in this proof, you just start with your root lattice that you actually use in the scheme, and you replace it by this auxiliary lattice, and then use these certain properties there to make the rest of the proof work. But this gives us the following security assumption that the scheme is hard if and only if, if this distinguishing problem between these two lattices is hard to solve. So you could say, as a goal, we would need to find such an auxiliary lattice with these right geometric properties to instantiate these schemes. And one example of this is like one that has a good packing or smoothing or covering. For this talk, you can just assume we want to find an auxiliary lattice with a good packing density. And this brings us to the question, like, when is this distinguishing problem hard? And we have already seen it in variants before, namely the determinant of the lattice. And this is something you can compute efficiently. So if you have two lattices that have a different determinant, then of course you can always solve this distinguishing problem easily. You just, given this other basis of the lattice in the middle, you just compute the determinant and check if it's equal to one or the other. So you could say that, if these determinants don't match, then the distinguishing problem can be solved efficiently. And more generally, this means that this auxiliary lattice must have the same efficiently computable invariance. So the determinant is just one example of such an invariance. And this brings us to the genus of a lattice. And for this, there's like a small technical note that we only consider integral lattices, those with where all the inner products between pairwise lattice points are integer. And then we can define the genus as of a lattice, or like two lattices are in the same genus, if and only if they are equivalent over the p-adic integers for all primes p. In the last talk of this session, we'll go way more about the genus, so I won't go into more detail about this precise definition for now. But some facts about this invariant is that any genus contains only a finite number of isomorphism classes. And secondly, this genus equivalence is efficiently computable. It might look a bit weird because you have an infinite number of primes to check in some sense, but it turns out you only need to check a finite amount, and yeah, that's efficient to do if you know the factorization of the square of the determinant. But I will push that aside for now. And what's the most important for us is that this seems to cover all the other invariants that we know that you can efficiently compute over lattice. I placed a small asterisk here again because in the last talk you'll see something about like what's called the spinor genus of a lattice, which is slightly stronger, but in this setting these always are the same, so that's not a problem for us. Okay, so we have now these genus, and these are the invariants that we are kind of constricted to. Like we need to find an auxiliary lattice that matches on the genus, but that still has these good packing properties. And this is not just like a theoretical thing. Like if you look at these constructions, these schemes, in these papers, they really have these requirements. So, for example, in this one paper, they need a first minimum that is within the square root of log n of this upper bound. And in this other paper, they need a first minimum that is within the fourth root of n from this upper bound. And also in our work, we, if you would like have something that even lies within a constant factor from this Minkowski bound, we will be able to get a way more efficient construction. So what we actually need is a Minkowski-Lafka-like theorem within a fixed genus. And remember the argument from before, we looked at the random case, that behaved quite well, and from that we showed the existence of a good lattice packing. So we'll try to repeat that argument, but for example, first we need to define like what does it mean to be random, like what's a random sample over a genus. And for this, let's first look at this following Moss formula, which is already like from Siegel in 1935, so it's a really old result. And this says that any genus contains a finite number of isomorphism classes, and we have this quantity called the mass of a genus, which is just the summation over all these isomorphism classes of 1 over the size of the autophism group. And this is a quantity that in general you cannot like compute just by kind of enumerating the genus because it can be very large. But this total mass is something that is, we have formulas for this. It's something that is efficiently computable, which to me is quite surprising. But using these formulas, we can also see that this mass actually grows very quickly in the dimension. So in some sense, the genus, all these p-adic equivalents, it sounds very restricting, but it seems that there are still an enormous amount of lattices that fall into the same genus. And that's good news for us, because if we have more lattices, we have a higher chance to actually find a good one. And this also immediately defines kind of a natural distribution on the genus. Namely, every lattice we just give as a weight 1 over the size of the autophism group, and we sample with respect to that weight. And then, of course, the question is, do these actually behave like random lattices? Like, are they good lattice packings on the average? Our main result is that they are. And this gives us the following Minkowski-Lafka-like theorem for a fixed genus. So let G be any genus of dimension at least 6. And here we have some kind of small technical assumption that we need on the genus, but you can forget about that. For now, it's really not something that's going to be a problem for essentially any lattice that you want to use this on, or any genus. And we have this small constant. Then we show that there exists a lattice in this genus where the first minimum is essentially equal to, or like at least the half times this Minkowski bound. Note that if this constant c will be 1, we get precisely the Minkowski-Lafka theorem, and here it's like slightly smaller, but it's also within like the 2 over the power to 2 over n, so that completely disappears once you increase your dimension. So this essentially matches the packing density of like fully random lattices without this constraint on the genus. And we can even show like similar results where you get both a good packing in the primal lattice and also in the dual at the same time. We can also generalize it not to just like having the existence of 1, but we can say if we decrease the bound that we want to achieve by a little bit, let's say by 0.95, then we can show that all but a negligible amount of like the mass in the genus attains a good lattice packing. So these are really kind of strong results. They really say that almost all the lattices in the genus are really good. And these results also, we can get similar results. I haven't defined what it is, but for the smoothing parameter of a lattice, and also for getting good lattices that have a good covering radius. So this is the result, but let's look at the proof of it. I won't go into all the details, but what we've seen before is that we needed some kind of way to count the average number of points in this ball. And we would like to do the same over a genus. And this is precisely where the Siegel-Well mass formula, which again, a very old result from the 30s, 40s, comes into play. And this mass formula says that if we take some squared norm m, and we look at all lattice points that have this squared norm, and we count them, then the average over the genus is something that is efficiently computable. Again, we have formulas for this, and we can compute it. And this is for me a very surprising result. Like this genus seems to be a very big thing, kind of complicated, but again, in the average, we have formulas for it. And this gives us precisely this average case counting result that we need. And what we also need to show is there are not that many points in this ball. So in this case, we need to show there are not that many vectors of squared norm m. And we show in the paper like the following upper bound under these like technical constraints, or under this technical assumption. But these technical assumptions are really like we can get rid of them by losing a little bit, or we can make them slightly stronger and improve the constant, but they're not so important. And with this upper bound, we can just do a similar proof as in the Minkowski-Lavka case. Like we look at the average number of lattice points up to a certain bound, and show that this is less than 3, and therefore there must exist one that gives a good packing. Okay, so let me conclude with that the genus is the strongest known efficient invariant for lib that we know, and it has actually been well studied from a mathematical perspective long ago already. I mean, essentially all the results I used for this work are from before like the 1950s. And for one of these results, so thanks to the Smith-Minkowski-Siegel mass formula, we know that any genus contains a finite but typically very large number of isomorphism classes, and it gives us kind of a natural notion of randomness over such a genus. And thanks to the Siegel-Well mass formula, we can show that in any genus there exists a good packing, like lattice packing, both in the primal and dual. There exist lattices with a good smoothing parameter, there exists lattices with a good covering radius. And in fact, you can even argue that there exists a lattice that attains all these properties at the same time. And this is very useful for instantiating all these lib-based schemes. So just as a general takeaway message from this talk, you can think of random lattices within a genus essentially behave like random lattices, like fully random lattices. And thank you for listening.
Thank you, Vessel. Any questions from the audience?
Thank you very much for your talk. Well, maybe a bit unrelated question, but I'm not aware of any concrete instantiation of an algorithm that breaks lattice isomorphism problem. Could you please elaborate a bit on how to break Hawk, for instance?
Okay, so for the specific case of Hawk, we essentially work with a structured version of C to the n. And for the lattice C to the n, finding the orthonormal transformation is essentially equivalent to finding the shortest vectors of the lattice. Because once you have the set of shortest vectors, you can map them in any way to the unit vectors of C to the n, and it will recover it. So the best way we know at the moment is really to find the shortest vectors, and that's just like by usual lattice reduction techniques. There have been some works recently on the structured variants of the problem, where you can, for example, abuse the fact that if you have a rank 2 module over like a totally real number field, then you can do some more tricks, but those all don't seem to be applicable, at least for now, to the Hawk case, which is over cyclotomics with a totally imaginary field. Yeah.
Sorry. And in order to assign norms of the shortest vectors, one would need to use graph theory, right?
So for Z to the n, no, because it's kind of trivial, like all the assignments work. But in general, yes. So in general, you could reduce, like if you, once you find this kind of some kind of large set of short vectors, you can kind of turn it into a graph isomerism problem, but the graph can be very large. But there are also better algorithms to do this, asymptotically at least. Like there's a work by Vadim Lyubashevsky, where they give like an n to the on algorithm to solve lib. But in practice, you would more do like this algorithm by Pleskin and Souvier, which kind of just tries to make all these appointments kind of a branch and bound technique.
I see. Thank you.
Any other questions? Yep.
Good, thanks. Yes, a very interesting talk. Yes, and so you wanted to find the genius to give something like a decision problem in the LIP, or because I saw that in your slide, and you introduced that in a genius there are finite class of the finite class of isomorphism. Yeah, so if it's possible to give a decision problem like this so that we can use using the design of another schemes based on the genius.
So you mean like, can we
construct another schemes because it's something like a decision problem. Is it a decision problem or basically?
You mean like within a genus, or?
Yes, yes.
Yeah, so if you do some kind of decision problem, I mean, you can just define the decisional variant of lib, but then you also need to make sure you work within one genus, because otherwise, again, it's going to be like efficient to solve.
Okay, I see. Thanks.
Let's thank Bessel once more.
Do you hear me?
Okay, so the next talk is an online talk, and it's on the cryptanalysis of rank 2 module lib with symplectic automorphisms by Hengyi Liu, Kaiji Jiang, Anbin Pan, and Anyu Van. And I guess Hengyi will give the talk.
Okay, can everyone hear me?
We can hear you, go ahead. Okay, now we stopped hearing you. Is it our problem or?
Is here okay?
Yeah, yeah, now we can. Go ahead.
Okay, okay, okay. And today I'm excited to share our work on cryptanalysis of rank 2 moduli with symplectic automorphisms. This is a joint work with Kaiji Jiang, Yanbing Pan, and Anyu Wang. Let's start with some background. In the second round of the NIST submissions edition call for signature schemes, HOC was the only lattice-based signature proposal that advanced. Its security relies on the hardness of the lattice isomorphism problem. For simplicity, we call it LEAP. To explain briefly, the lattice isomorphism problem involves two lattice bases, C sub 1 and B sub 2, of isomorphic lattices. The task is to find an isomorphism, which means finding an orthogonal matrix O and a unimodular matrix U, such that B sub 1 equals to O times B sub 2 times U. When viewed through the Gram matrices of bases, they differ by a unimodular congruence transformation, indicating their equivalence as quadratic forms. This is laterally to the quadratic form version of LEAP. There is a lot of work related to LEAP, including algorithm and cryptography. In cryptography, once a general lattice problem like LEAP is defined, a common approach is to consider the structured lattices, which leads to the module LEAP. To define module LEAP, let me briefly introduce some concepts from number theory. A number field K is a finite extension of rational numbers Q. Its ring of integers O sub K is a lattice under the canonical embedding. A module lattice over O sub K is a finitely generated module in K to the L, which has a form like B sub 1 times I sub 1 plus and so on B sub R times I sub R, where the B sub I are vectors in the K sub L, and I sub I are contained in the K are the O sub K ideal. When all the ideals I sub I equals to the OK, we call the module a free module. And we call the R the rank of this modulities, and usually consider the case when R equals to L. For rank 2 free modulities, the quadratic form version of module LEAP can be stated as follows. Given B and G in the GL sub 2 over K, the task is to find a U in the GL sub 2 over the O sub K so that BU star times BU equals to G, where the star denotes the conjugate transpose. The definition of module LEAP for the general module lattices was given by Muriel et al. Not much work has been done on module LEAP. For algorithms, there are some works of LEAP for lattice with specific symmetries, such as ideal lattices in such a quotient of polynomial ring. And at Asiacrypt 2024, Muriel et al. Proposed a heuristic probability algorithm to solve rank 2 moduli in totally real number fields, which runs in polynomial time for a large class of inputs. And for conduction, the signature scheme fork we mentioned before is built on the hardness of the moduli for the module O sub K squared where the K is the cyclotomic field with conductor of power of 2. Now, let me share our contributions. First, we propose a probable deterministic polynomial time algorithm to solve moduli for rank 2 modules, which M contained in the K squared, where K is a totally real number field. Second, our work invalidates the almost SVP assumption used by Hawk to argue its forgery security. Importantly, we stress that our work results haven't yield any extra attack against Hawk. The key to our approach is a new lattice automorphism for rank 2 module lattices. Lattice automorphism, in simple terms, refer to finding an isomorphism of lattice to itself. Here, both the corresponding orthogonal matrices and the unimodular matrices are regarded as lattice automorphisms. More specifically, the unimodular matrices can be understood as automorphisms of quadratic forms. Note that the unimodular matrix being a quadratic form automorphism if and only if it preserves the inner product induced by the quadratic form. Now, why do we focus on lattice automorphisms? First reason, lattice automorphisms reveal the symmetry of lattices, and there has been extensive research on using these symmetries to solve leap of certain lattices. And in Asiacrypt 2023, Jiang et al. Demonstrated that if we can identify non-trivial lattice automorphism for the input of the leap of integer lattices, we can solve that kind of leap. And in the case of Hawk, the lattice O sub k squared has known lattice automorphisms. That is the scalar matrices of root of unity. And the forgery security of Hawk is based on the hardness of one more SVP, which implied the difficulty of computing other lattice automorphisms. So this things bring up a natural question. Does the algebraic structure of O sub k squared provide us with more lattice automorphisms? The answer is yes. To show this automorphism, first we introduce some notations. First, let J sub 2 be such a matrix which has a form like symplectic form matrix. And let L be the same number field, such as cyclotomic field, and B in the GL sub 2 over L, U in the GL sub 2 over the O sub L, G prime equals to the BU star times BU. And we can define the Q linear map T star like this. It's just conjugate on each component. For quadratic form G prime equals to BU star times BU, we claim that BU's inverse times J sub 2 times J star times BU is a lattice automorphism. The following calculation supports this assertion. However, it should be noted that some terms are slightly missing here. For general lattices, this operation does not necessarily map the lattice vectors to lattice vectors. In our paper, we refer to it as a pseudo-lattice automorphism. For simplicity, we ignore this distinction here. To compute the above lattice automorphism, we use the following proposition. Given BU star times BU and B, to apply this proposition, we only need to compute the determinant of BU, or just determinant for U. First, we can calculate the determinant for U times determinant for U star. And we also know the principal idea induced by determinant for U is just O sub k under the free module leap case. Finally, based on previous results, we can determine the determinant for U up to multiplication by some root of unity. For general module leap case, a more detailed argument is needed to obtain the principal idea induced by determinant for U. As applications, the above lattice automorphism invalidates the ORM SVP assumption used in the Hawkes forgery security analysis, although it does not yield any direct attacks against Hawkes itself. But it may help the set kernel attacks. For example, in this work, it is necessary to get the preimage of two vectors. While using the lattice automorphism, we only require guessing preimage of one vector. And finally, in the case of totally real number field, this approach can apply to solve rank 2 module leap. Finally, let's briefly introduce the main idea of the polynomial time algorithm for rank 2 module leap in totally real number fields. A number field K is called totally real number, totally real, if every embedding of K into the complex numbers maps the field to the real numbers. For example, the K equals to some cyclotomic field intersection of the real numbers. In this case, P star is commutative with BU. This means what we actually obtained, the lattice automorphism is transformed to the J sub BU equals to the BU's inverse times J sub 2 times BU. And recall the problem definition. Assume K is a totally real number field, and L be the extension of K with imaginary unit. Given B and G prime in the GL sub 2 over the K. And there is a U in the GL sub 2 over the O sub K, such that BU star times BU equals to G prime. The goal is to find such a U. Naturally, first idea is this. Combine the J sub BU with the diagonal matrices like this, and we can use the existing algorithm. For the O sub K squared case, this works, but for general case, it doesn't. The reason is simple. Previous algorithms rely on strong symmetries in the lattice structure, which are not always present in the general case. Here's a second idea. Recall that BU transform O sub L squared into B times O sub L squared. The question is, can we find a submodule M contained in the O sub L squared and M plus contained in the B times O sub L squared with lower rank, such that BU transform M to M prime. We approach this by using eigenspaces. Let E sub lambda denote the eigenspace for eigenvalue lambda. We know that the 2x2 matrix J sub 2 and the J sub BU both have the eigenvalue plus or minus I. It turns out that the E sub I of J sub BU intersection of the O sub L squared satisfies the conditions for the submodule lattices. The remaining part is how to deal with the rank 1 moduli in the same number field, mainly using the previous work, as well as some little tips. To put it simply, the algorithm can be broken down into 3 steps. First, we compute a module lattice automorphism. Then, we use the eigenspaces of this automorphism to identify 2 isomorphic submodule lattice. Finally, we solve the isomorphism problem on these submodule lattices, which allow us to recover the original isomorphism. Finally, we note that the previous algorithm can replace J sub 2 with a modular case to get such a reduction. We can replace J sub 2 with the unitary matrix over the O sub M. That's all. Thanks for your attention.
Okay, let's thank this. Okay, you did. Do you have any questions from the audience? Yep.
First, I would like to thank you for your talk. So, you have claimed that one of your contribution is coming up with a provable deterministic algorithm for module leap over totally real fields. Well, as to me, as far as I can recall, Pelé-Marie et al. Have already come up with a provable, maybe not deterministic algorithm. So could you please clarify why are you doing better? Thank you.
Hey, you're on mute here. Can you? You have to unmute your microphone. No. Yeah, we can't hear. Okay.
Okay. The main reason is the methods used by Pelé-Marie et al. Are number theory methods, and they mostly focus on the local. They just solve the problem of the square sum of 2 algebra integers. Our methods consider the 4 lattices and use the symmetry. That is the new automorphism so there is a totally distinct method between we and theirs.
I see. Thank you.
Is there another question from the audience? Maybe, okay, maybe I can ask a question. So you say you invalidate one of the assumption that Hawk uses is in its security proof, but doesn't break Hawk. Can Hawk be based on a different assumption to claim security?
Yeah. They can just add our new short vectors to their assumption. That's okay. But this is a need to consider problem. But for our break, they only need to add the new short vectors used by our automorphism. That's okay.
Okay, thank you. Any more? Nothing? Okay, so let's thank the speaker one more time.
Thanks, Vadim. Thanks, everybody.
Hello? So do you guys hear us online? The speaker? Andrew? No? Andrew, I think you're muted and the video is not on. Can you unmute yourself? You're still on mute. Sorry? You have the video. Oh, okay. So Andrew, we're being told we have the video of your talk, so we can just play it. And then maybe at some point you come on for questions if you want. So we're going to do that now.
Genus and the distinguishing lattice isomorphism problem. So what is this lattice isomorphism?
Okay, so we have the video.
Hi, I'm Andrew Mendelsohn. I'm a postdoc at Imperial College London, and I'm going to talk about some joint work with Zhongling and Jingbo Liu. This work is called On the Spinor Genus and the Distinguishing Lattice Isomorphism Problem. So what is this lattice isomorphism problem? Well, it's to decide if two lattices are isomorphic, and if so, find an isomorphism. One way we might seek an answer to this, possibly a negative answer, is to compute arithmetic invariants. These are efficiently computable properties of lattices preserved under isomorphism. This means that a lattice L and its image under some isomorphism F share this efficiently computable property. Two examples are the class and the genus. So we say two lattices are in the same class if they're related by some global isomorphism, and we say they're in the same genus if they're related by local isomorphisms and over the reals. One of the questions which motivates this work is, are there more such relations? It turns out the answer to this is yes, and in this talk we'll talk about a certain invariant called the Spinor genus and when it can be used to solve the lattice isomorphism problem, and in particular decision or distinguishing variants of that problem. To provide some motivation, The reason we care about understanding these problems is because cryptography has been built whose security is based on these problems. So we have key encapsulation, signature schemes, PKE, the security of which is based on LIP. In particular, this paper from 2022 developed a signature scheme called HAWK, which is part of NIST's post-quantum cryptographic standardization process for signature schemes. So we really care about understanding the underlying hardness of these problems. So what is a lattice? Well, a lattice is an integer linear combination of some basis vectors bi. We can put these bi as the columns of some matrix capital B and then represent lattices with such a basis. You can see an example of a lattice in the bottom right-hand side of the screen. And we can also define transformations on lattices. So the space of invertible matrices of determinant plus minus 1 will be called GLNZ, and the orthogonal group of matrices are matrices such that their product with their transpose is the identity. We can then define lattice isomorphisms by saying that two lattices L and L' are isomorphic if and only if there exists some orthogonal transformation that maps one lattice to the other, that maps their bases to each other. We can then use this to define an equivalence relation and partition the space of integer lattices by this equivalence relation to obtain equivalence classes. And we'll use these square brackets to denote the class. We also might write L in class of L'. Using this, we can define our lattice isomorphism problems. So there's a search problem, which is to find a unimodular matrix U and an orthogonal matrix O that connect the bases of L and L' as B' equals O B times U. And we ask for this U because otherwise the problem becomes tractable. We can then define two kind of decision style problems. So the first will be called decision lip. And this is to decide if such a pair UO exists for given lattices L and L', but you don't have to find such an isomorphism. The second problem is going to be called distinguish lip. So this is given L0, L1, and L, so three lattices, and the promise that L lies in the same class as either L0 or L1, uniformly chosen. One then has to find this bit B with non-negligible advantage. So pictorially, what's going on? Well, here we have two lattices. They're given by two basis vectors each, and one has to decide if they're related by some orthogonal transformation. In this case, they're related by a 90-degree rotation, but in higher dimensions, the problem might not be so trivial. We'll also need to talk about quadratic forms. So what is a quadratic form? Well, it's a homogeneous polynomial of degree 2 with some coefficients Fij, satisfying this symmetry law that Fij equals Fji. So we can write it out in the form on the second line. And we can also write it in a third form, which is f of x, where x is a vector of variables, x1 up to xn, equals x transpose capital F times x. And here, this capital F is a symmetric matrix which defines the quadratic form. And we then say two quadratic forms are equivalent over the integers if there exists a unimodular matrix U such that F equals U transpose GU, for capital F and capital G being the corresponding matrices of our quadratic forms. And we then have some notation which denotes when two quadratic forms lie in the same class. The reason that we are talking about quadratic forms is that one can essentially move between the world of lattices and the world of quadratic forms. If we're given two lattice bases that represent lattices in the same class, we can form equivalent quadratic forms from those bases and vice versa. So we might move interchangeably between the world of lattices and the world of quadratic forms in this talk. We're really talking about the same thing. So back to arithmetic invariance. The decision and distinguish problems are easy, the lattice isomorphism problems, if there exists efficiently imputable invariants of quadratic forms which differ for forms in different classes, i.e. if the forms or the lattices are not isomorphic, then these invariants differ. An example of this is the determinant. So if we take equivalent quadratic forms and just take the determinant of their of both sides of the relation, we find that this determinant is the same. So there is some fingerprint, i.e. some set of invariants that are efficiently computable that we can compute on any quadratic form. And if we're going to use LIP in cryptography, we really need to make sure that two forms that are an instance of a lattice isomorphism problem have matching fingerprints, because otherwise the problem is straightforward to solve. We care in this talk about notions of equivalence, these the last entry of the fingerprint. So let's talk briefly about the genus. We'll define Z subscript brackets P to be the set of fractions whose denominators are co-prime to P. And we then say that F and G lie in the same genus if and only if the matrices of F and G are related by some unimodular transformation U subscript P in the following way: F equals UP G UP transpose for all primes and also over the reals. This is a kind of easier way of talking about the p-adics. And each genus is a disjoint union of classes. So given some quadratic form, we know that the class of F is contained in the genus of F. What we can then do is, given F and G, which represent some lattice isomorphism problem instance, some decision instance, say, we can test if the two forms lie in the same genus. If the forms don't lie in the same genus, then they don't lie in the same class, precisely because each genus is a disjoint union of classes. This notion has been studied in a cryptographic context, but our question is, are there more such equivalence relations on the space of quadratic forms? And moreover, are they useful for solving decision lattice isomorphism problem and distinguished lattice isomorphism problem instances? The answer to this question is yes. It's called the spinor genus. And here is a kind of big picture description of how it works. So we let V over K be a vector space over a field. There's then a homomorphism from the group of rotations of V, i.e. the orthogonal group on V, to the space of units of K modulo squares. This homomorphism has a kernel. This kernel is a normal subgroup of the group of rotations of V. In the case when it's a proper normal subgroup, we can use it to define an equivalence relation on lattices in V. And in particular, we'll use this homomorphism from the group of rotations of Vp to some space modulo squares to define an equivalence relation on lattices in V. The partition that you get from modding out by this relation gives you a relation of a set of classes which are finer than the genus but coarser than the class. So we get an intermediate relation. So to kind of illustrate what's going on, here I have some drawings. So we have some space of lattices which we can partition into two genera. We have genus 1 and genus 2. Each genus is a disjoint union of spinor genera, so we can partition each genus into two spinor genus in this example for simplicity. Because both the spinor genus and the genus are disjoint unions of equivalence classes, we can then have the equivalence classes class 1 and class 2 lie entirely within spinor genus 3 and 4. So suppose we have two lattices, L1 and L2. We can compute whether or not they're in the same genus or not, and in this instance we find that they are, so this doesn't help us solve the distinguishing problem. What we want to know is if they're in the same class. In this case, they're not in the same class, but we can't compute that because that's the intractable problem we're talking about. But if we could compute the spinor genus, we would be able to tell that they're in different spinor genera and therefore in different classes. And this is kind of what's the idea of what's motivating this work. So let's define the spinor genus. Here is our setup. Let K be a number field and take V to be a vector space over K, and we'll take our lattices to live in this vector space phi. A vector space equipped with a quadratic form phi is called a quadratic space. This form maps you from V to the underlying field K, and we can define the orthogonal groups on this vector space. So the orthogonal group of V will be a set of linear transformations from V to V, such that phi is preserved under transforming its argument by this transformation. So phi of sigma x equals phi of x, and this group contains a subgroup O plus of V, which is the determinant 1 elements of the orthogonal group. We will also need two basic definitions on quadratic forms. We'll say a quadratic form is regular if its determinant is non-zero, and we'll say a form is anisotropic if there is no non-zero vector that evaluates to 0 under phi. We can then redefine our notions of class and genus using this vocabulary. So two lattices, L and L dash, lie in the same class, if and only if there exists some orthogonal transformation that maps L to L dash. And these lattices lie in the same genus, if and only if there exist B to P, which are in the orthogonal group of the localization of V at P, such that L dash is mapped, or L is mapped to L dash by B to P for all primes P, and also over the reals. So we'll now need to define the spinor norm, that homomorphism I talked about earlier. So we'll let B of xy be the corresponding bilinear form to the quadratic form phi using this polarization identity. So B of xy is half of phi of x plus y minus phi of x minus phi of y. And we'll then define a reflection. So a reflection is an involution tau, i.e. degree 2 map, which is defined by some anisotropic vector y, such that for all x in V, tau of x is given by x minus b of xy over phi of y times y. And because this reflection is defined entirely by y, we'll subscript the y and refer to these reflections by tau subscript y of x. There's then a theorem by Cartan and Giudone which says that if we have an n-dimensional regular quadratic space, V phi, then every element of its orthogonal group is a product of at most n reflections. Using this, we can then define the spinor norm. So we're going to take some orthogonal transformation of determinant 1, so an element sigma of O plus V. By Cartan Giudone, we can then factor this sigma as a product of tau yi, where I runs from 1 and up to n. We can then define a map theta, which maps you from O plus of V to the space k units of k modulo squares, where we map sigma to the evaluation of phi at the yi that define the reflections that sigma factors into, and take this product from I equals 1 up to n. This is then a multiplicative homomorphism called the spinor norm, and it has a kernel denoted by capital theta of V, which is a normal subgroup of the proper orthogonal group of V. We will then use this to define an equivalence relation using the localizations of V at P in a similar manner to how the genus is defined. So let's define it. We'll say two lattices, L and L dash, satisfy the relation S if there exists some gamma in O plus V and delta P in the spinor kernel at P for all P, such that L dash equals gamma delta P L. One can see that this is an equivalence relation intermediate to the class and the genus as follows. So suppose delta P were the identity matrices for all P. We would then have that L dash equals gamma times L, and that is simply the definition of the class. Similarly, if gamma were the identity, we would have L dash equals delta P times L for all P. And these delta P are elements of O plus VP. So this is similar to the definition of the genus. I won't go into the detail, but one can see that this is an equivalence relation. And the key thing here is that transitivity uses this normality of the spinor kernel when proving that L, L dash, and L dash dash satisfy the transitivity relation. We can then use our relation S to define the spinor genera. So we quotient the space of lattices by this relation S and get a set of equivalence classes, which we call the spinor genera. And if the relation holds on two lattices, we might also write that L is in SPN of L dash for spinor. Some basic properties of this relation then, some basic properties of the spinor genus. So the first is that the number of spinor genera in any genus is finite in a power of 2. And for all n at least 3, there exist lattices whose genus contains multiple spinor genera. So this tells you that the spinor genus really is something different to the genus. Finally, if we take a quadratic space of at least dimension 3, a lattice in that space, and assume that phi takes integral values on L, then if the genus of L contains multiple spinor genera, either there exists some odd prime P that divides the determinant of L to some large power, or there exists some large power of 2 that divides the determinant. And this is useful in the context of the lattice isomorphism problem because we can compute the determinant of our lattice, and if no such primes divide its determinant, then we know that its genus will not contain multiple spinor genera, and we cannot use the spinor genera as a distinguishing tool. So, for the rest of the talk, I want to talk about our contribution, which is to create an efficient quantum algorithm that tells if two anisotropic binary quadratic forms over the ring of integers of some number field lie in the same spinor genus. So let's begin by considering the simplest case. Primitive integral binary quadratic forms f and g over z. Here primitive means that the GCD of their coefficients is 1. There's a theorem by Estes and Poole from 1973 which says that if f and g lie in the same genus, then they're in the same spinor genus if and only if they satisfy f equals g times k to the 4 for some form k under Gauss composition. One can rewrite this in terms of lattices as follows. We say that two lattices L and L dash are in the same spinor genus if and only if L dash inverse times L lies in the 4th powers of the class group of the left order of L dash. Now, there's some jargon there. But the point on this slide is that we can take our problem defined in terms of quadratic forms and transform it into a problem in class groups. The question this raised, that motivated our work, is can this be extended to forms over number fields? And if so, can it be computed efficiently? On that second point, the reason our algorithm is a quantum algorithm is because we will use the following theorem by Bias and Son, which this theorem says that under GRH, there is a quantum algorithm for computing the class group of an order in a number field, which runs in polynomial time in the degree and the log of the discriminant. So when the discriminant of the order is not too big, we get an efficient algorithm, a quantum algorithm, to compute class groups. And we will use this as a kind of underlying ingredient in our algorithm. So what other ingredients do we need? Well, we'll let f and g be anisotropic binary quadratic forms over the ring of integers of f. This means that f and g correspond to lattices of rank 2 over OF in V. Because of our conditions on f and g, we can take V to be a regular binary quadratic space over a number field f. In this case, we can fix a basis such that V is isomorphic to a field extension, a quadratic field extension of f, defined as f adjoined the square root of minus d for some d. What this means is that we can multiply elements of V by one another. So it's not just a vector space, it's also a field. We'll write O of V for the ring of integers of this field. Finally, we'll define the left order that we saw on the previous slide. So the left order of a lattice, say L2, is the set of elements in V such that x times L2 maps you back into L2. And it's a fact that any lattice is a left ideal in its left order. We will need the following two lemmas. Lemmas by Ernest and Estes, the first from 1980, which says that a necessary insufficient condition that L1 lies in the same spinor genus as L2 is that L1 times L2 inverse lies in the spinor genus of the left order of L2. The second lemma says that if the ring of integers of F is a principal ideal domain, and we have some order of degree 2 over the ring of integers of F, then this group, H of O, is isomorphic to the squares of the class group quotiented by the fourth powers of the class group. And this group H of O is the genus quotiented by the spinor genus. When one combines these together, one finds the following: that the spinor genus of O, quotiented by the proper or the class group of O, is isomorphic to the ideal class group raised to the fourth power. So the fourth powers of the ideal class group. And if we have two lattices, L1 and L2 in B, and these lie in the same genus, then they're in the same proper spinor genus, if and only if L1 times L2 inverse is a quartic residue in the class group of the left order of L2 and B. So there's some, it's a fairly technical slide, but the point here is in this last line. So what this says is that, like for forms over the integers, if the ring of integers of F is a PID, we can convert our problem for quadratic forms into a problem of fourth powers in a class group. So here is our theorem. We let the ring of integers of F be a PID. We let F and G be anisotropic integral binary quadratic forms over the ring of integers of F in the same genus. We then let V be the quadratic space containing the two lattices LF and LG corresponding to F and G. Then, if LF times LG inverse generates an ideal coprime to the conductor of the left order of LG in the ring of integers of V, then we get a quantum polynomial time algorithm to decide if F and G lie in the same spinor genus. And this condition that LF times LG inverse generates an ideal coprime to the conductor is some mild technical condition. So we'll run through the proof in the simple case that the left order of LG is maximal. In this case, the technical condition on the conductor kind of disappears. So how does the proof go? Well, F and G are anisotropic. This means that the corresponding lattices lie in some vector space, which is also isomorphic to a quadratic field extension of F. We then compute a basis of the left order of LG and compute the class group using that quantum algorithm on the previous slide. This gives us a set, generating set of prime ideals for the class group of the left order of LG in quantum polynomial time and their defining relations. These relations form a lattice lambda, and the class group of the left order of LG is isomorphic to z to the n modulo this relation. The way that this isomorphism works is that we take some ideal in the class group, we factor it uniquely into a product of prime ideals with some exponents, ei, and we map I to its tuple of exponents E1 up to En, and then mod out by the relations lambda. Zn modulo lambda is an abelian group, so we can write the class group of the left order of Lg as some direct sum of abelian groups, Z mod Diz. These factors Di are given to us by the quantum algorithm. And for the rest of the proof, we want to understand the image of Lf times Lg inverse in this direct sum of abelian groups. So we assume that the left order of Lg is a maximal order. This means that we can write Lf times Lg inverse as an ideal in this order and factor it into a product of primes in our generating set and then reduce modulo the relations between the prime ideals. This allows us to map Lf times Lg inverse to its corresponding tuple of exponents, as in step 2, call these exponents f1 up to fn, modulo the relations lambda. The quantum algorithm also gives us some vectors gi bar. These are of order di, and they form a basis of Zn modulo lambda. We can then test for quartic residuosity. We proceed as follows. We write our tuple of exponents, f1 up to fn, as a linear combination of these basis vectors, gi bar, with some coefficients lambda I. We can then write the gi bar as the columns of some matrix G and invert G on this expression to obtain G inverse times f1 up to fn transpose equals our vector of coefficients lambda. If each entry in this vector of coefficients, say lambda I, is equal to 4 times gamma I modulo di, for some gamma I in Z mod diz for all I from 1 up to n, we can conclude that Lf times Lg inverse is a quartic residue in the class group of the left order of Lg, because in some sense these coefficients are fourth powers. We can then use this result to conclude. So we say that use the lemmas by Ernest and Estes to say that if Lf times Lg inverse is a quartic residue in the class group of the left order of Lg, then F and G lie in the same spinor genus. Otherwise, they do not. So what are the consequences of our theorem? So these first two lines just describe the same setup as we had for our theorem. Our first corollary is as follows. Suppose that the size of the class group of the left order of Lg is odd, then F and G lie in the same spinor genus. And this kind of tells you when this is not so useful, because if this class group has odd cardinality, then we don't really get any information from the spinor genus. So let's move on to something more useful. Let F be the maximal totally real subfield of the nth cyclotomic field, and let n be a power of 2 up to 512, and assume GRH. Then we get a quantum polynomial time algorithm to decide if F and G lie in the same spinor genus, because the ring of integers of F is a PID, and the conditions of our theorem hold. And similarly, if we let F be the nth cyclotomic field, and n lie in this set, then we can apply our theorem again to obtain a quantum polynomial time algorithm to decide if F and G lie in the same spinor genus. Those are the corollaries from our theorem. I'd like to thank you for listening, and I'm very happy to take any questions. Thank you.
Okay, thanks. Do you know if the speaker is online or? Okay. Are there any questions for Andrew? Yeah, there's.
Yes, so thank you very much for your talk. So you said you have algorithm for cycloatomic fields of power of 2 up to 256. What does break for 512 cycloatomic field?
What breaks once you go higher than 512?
Yes.
So it's simply that it hasn't yet been proven that the class number of the maximal real subfield of the 2 to the nth cyclotomic fields for higher conductors are principal ideal domains.
I see. Thank you.
Any more? Okay, so thank you, Andrew, and let's thank Andrew again.